of very well-established symmetry that makes the integrals straightforward. Okay. Let's try some problems. So let's imagine that I have a current carrying wire. And I want to think about the magnetic field at 2 points on either side of this wire, point A and point B. You can see point A is closer to that current. What can we say about the strength and the direction of the magnetic field at those 2 points A and B? Let me bring up the poll. Remember, we just saw the magnetic field for a current carrying wire. It's equal to mu naught I over 2 pi r. All right. Most of you are selecting B here. Let's see if that's the case. Well, first of all, I can tell the magnitude, right? As R increases, the magnitude of B decreases. And so if I'm twice the distance away, I have to go down by a factor of 2. So it should be half as strong. So it's either A or B. Does the field point in the same direction or in opposite directions? Well, I can use my right-hand rule. I'm going to align my thumb with the current. My fingers are going to curl around in the direction of the magnetic field. So over here, the magnetic field's coming out of me, coming out of the page at me. Over here, the magnetic field is flowing into the page. And so I can see the magnetic fields point in opposite directions. What about this one? Now I've got this kind of funny shaped wire where I've got current going in this direction through the lower part of this funny shaped wire, and I've got current flowing in this direction in the upper part. What direction does the magnetic field point at this position P? Okay, let me go ahead and end the poll. Most popular answer was into the screen. Well, let's check. Let's call this the upper, or sorry, let's call this the lower path, and let's call this the upper. Let's find the magnetic field. What direction does the magnetic field point coming from that lower current branch? Well, I can use a right-hand rule. I can point my thumb in the direction of the current around that loop. So at the top of that loop, it points to the right. My fingers are gonna circulate around the current. So when I'm at P, it's gonna be pointing into the page. Now that upper loop then, B coming from that upper loop, the current's flowing in the opposite direction. And so I'm gonna get that the magnetic field points into the board. And then the total magnetic field is gonna be the sum of those individual contributions. So I need to know which one is larger, the magnetic field that points into the page or the magnetic field coming out of the page. Well, how do I determine that? Well, point P is closer to wire I and further away from wire R, and we just saw that the field falls off like 1 over R. So the field strength is weaker from that upper current because it's further away. So I get that the current has to flow into the screen. Sorry, not the current. The magnetic field has to be pointing into the screen. What about this one? Here's a loop, and I'm indicating the direction of the current flowing into the loop. So the current flows in on this side of this current carrying loop and comes back out at me on this side. Where's the magnetic north? Now, when we say magnetic north, we mean the magnetic north is just the side of this coil that has when I draw the magnetic field, the field is going to point through the center of this loop. The direction of the magnetic field points towards north. So which side is the north side of this loop? All right, let's go ahead and end the poll. Kind of split results between B and C. Let's see what's going on here. Well, let's see. If the current, let's do it. If we know I can point my thumb in the direction on that left-hand side of the loop, the current's flowing into the page. And so that means the field is going to circulate around the current like my fingers do. And so I'm going to get field that points downwards from the loop coming from this current. What about on the other side? So if that side where the current is coming out at me again, I point my thumb in the direction of that current, my fingers wrap around in the direction that the field points, and again, the field points downwards through this loop. Those sum together to give me a total magnetic field that points downwards through the center of this loop. So this is the north side and this is the south side. By definition, the thing that we call the north side compared to the south side, right? The north side is always on the right. South to north is the direction of the magnetic field. What about this one? Let's imagine I have a current carrying loop. So here's another loop and I bring a permanent magnet next to it. And I know that this is the south side and this is the north side of this permanent magnet. And what happens when I bring that magnet near that loop is I feel that there's a repulsive force, right? There's a force, this guy's being pushed away from the permanent magnet and the permanent magnet's being pushed away from that loop. Can we determine what direction the current is flowing in this loop? Okay, let's go ahead and end the poll. Okay, kind of split between current coming out at the top or in at the top. So let's see, if there's a repulsive force, that means this loop better generate a field that has something like the south side of that dipole field that's set up on this side and the north side here, so that the two south sides are together, would generate that same kind of repulsive force that I would feel from two permanent magnets that have their same poles pointed towards one another. So this means I need the magnetic field to point this direction through that current carrying loop. Now, what direction does the current have to flow to generate a magnetic field in that direction? Well, let's see, if current flowed in the top side of that loop, flowed in at the top, then I would use my fingers to circulate around in the direction of the magnetic field, and I would find that this is the correct direction. So I can see that the current has to be flowing in at the top. To get that magnetic field, I would have to have that current flowing out at the bottom. Another way we could do this, the right-hand rule also works for loops. If you wrap your fingers around the direction that the current is curling, and your thumb will point in the direction of the resulting magnetic field. So in this example, the current flows in at the top and out at the bottom. What about this one? So I have three different currents One of them is a mystery. I want to find this unknown current. And what I've already done is calculated the line integral, right? So the line integral is this thing B dot ds. Ampere's law told us that that has to equal to mu naught times the enclosed charge. Can we calculate what I3 has to be in this problem? What's that unknown current? Okay, let's go ahead and end. All right, so the most popular answer here was B, that it has to be 1 amp coming out of the screen. How are we going to do this? Well, this thing is the total enclosed charge. Well, I can see I1 is not enclosed in this path. So this total enclosed charge is going to be I2 plus I3. I can see that that has to sum together to be 7 amps. I2 is equal to 8 amps, so that means I3 had better be minus 1 amp. What does the minus sign mean? It means it has to point in the opposite direction of I2, so it has to be pointing into the board. So I get that the answer here is 1 amp into the screen. What about this one? If I calculate this path integral, we know it's going to be mu naught times the total enclosed charge. Which of A, B, C, D here gives me the correct expression for that total enclosed charge? All right, let's go ahead and end the poll. Most popular answer here was B. Okay. Well, we can eliminate some of them. So first of all, I can see that I1 and I2 point in opposite directions. So the signs on the current better be opposite when I put them into that law. So that one is not going to be the case. They don't necessarily have the same magnitude for the currents, so they shouldn't cancel out necessarily. They might if they were identical magnitudes, but we're not told that, so I'll eliminate A. So the question is the contribution to that path integral positive for I1 or positive for I2? Well, how am I going to determine that? Notice the direction that the path is pointed. They indicate a direction here. And for I1, right, my current is flowing in this direction. I can use my right-hand rule to determine that the magnetic field has to circulate around in this direction. And notice that the magnetic field is circulating around in the same direction as my path. So when I take this dot product, I'm going to get positive contributions. For this guy, that's the current's flowing in this direction, the magnetic field will point in the opposite direction against the direction that I'm moving around my path to calculate my integral. And so I'll get negative contributions to my, from this dot product because the B field and the path vector point in opposite directions. And so I need that I1 gives me a positive contribution, I2 gives me a negative contribution. So the answer has to be B here. Okay, what about this one? I have two of these solenoids, right? These coils of wire that I'm putting current through. And I put the same amount of current through each one. And one of them has twice the diameter, right? The loops are wider, has twice the length. And when I say the length, I mean this total length of this coil. We'll call it little l. And twice as many turns. Okay, so if I count the number, right? If I count the number of loops there, that one's in one and this one's in two. How do the fields running through the center of those solenoids compared? Well, we saw the formula. It said that the magnetic field through the center of a solenoid is just equal to mu naught times that current times the number of coils divided by 2 pi L, something like this. I'm checking. Actually, no, the 2 pi part is gone in this. I was worried about that 2 pi. Okay. So how do these compare? Can we calculate that? Okay, let's go ahead and end the poll. Most of you selected C, that they're equal. Okay, right. Notice again, I can rewrite this like mu naught n over L. That's just the density of the turns through in this solenoid times I. Well, I is the same for both of them, and this ratio of turns to length is identical. I doubled the number of turns as I doubled the length. There's no dependence on the diameter, so I end up with the same magnetic field through the center of each of these. What about this one? Here's a solenoid, and I see the direction of the magnetic field pointing through the center of this solenoid. Can you determine what direction the current is flowing around this solenoid? Where does the current, through which one of the wires is the current flowing into that solenoid? Okay, let me go ahead and end. Most of you selected that it enters on the right-hand side and leaves on the left. Well, let's see. If it enters on the right-hand side, that means the current is flowing in this direction. I can use my right-hand rule. I can curl my fingers in the direction of the current, so it goes behind the solenoid to start and then wraps around. My thumb points in the direction of the magnetic field. Right, so this gives me the correct answer. I could also just look at the current, right? I know on this face, if it comes in this side here and goes behind the wire, then through each of these segments that I see that are pointing towards me, the current is flowing down. I can use my thumb to point down in the direction of the current. My fingers wrap around that current carrying wire in the direction of the field. And again, in the center of the loop, the magnetic field points in the correct direction, points from left to right. Okay. So we've established now that we can generate magnetic fields by moving particles, and we can arrange moving charge particles in current carrying wires and use that to engineer interesting magnetic fields that might be useful for specific applications. Well, now we can think about what is the impact of a magnetic field on some other objects that are exposed to that magnetic field. And the most fundamental relationship you can find is that if I take a charged particle and I move it through a magnetic field, what happens is that charged particle experiences a force. And the relationship between all that is given by this simple formula. It says the force that that charged particle experiences as it moves through the magnetic field is equal to the cross product of Q times its velocity vector times the magnetic field. Okay. So what does this mean? That means if V is larger in magnitude, the faster the particle is moving, the larger the force that it experiences in the magnetic field. If Q is larger, the more charge, the larger the force. If B is stronger, it increases the force. And this is a cross product. So remember, a cross product tells me the magnitude of the force would be like QVB times the cosine of the angle between them. So it also depends on the orientation of V and B. Okay. If the velocity is aligned with the magnetic field, then I don't get a contribution. There's no force applied. If the velocity is perpendicular, that's when I get my strongest magnetic field. Sorry, I've got the wrong trig function here. This has got to be a sine theta. If theta is equal to 0, if B and V are aligned, then I want that thing to go to 0. So that better be sine. Sorry about that. And I can determine the direction of the force using the right-hand rule. Again, this is a cross product. Right-hand rules work generically for cross products. You always align your index finger with the first vector in the cross product. That's QV. So it's a positive charged particle. So in this instance, I would point my index finger in the direction of Q times V. I would point my middle finger in the direction of V, which is into the board. And then my thumb gives me the direction of the result of the cross product, or the force that points upwards. And I could extend that idea, right? I can think about a current carrying wire here as just again, a collection of a bunch of moving charged particles. So if I put those moving charged particles into a field, they're going to exert a force on the wire. Each of those individual charged particles moving in that wire experiences a force that's going to point to the left here in the setup that I have. What's the total force acting on the current carrying wire? Well, it looks like a cross product again. It's the current times L, which is L is the direction that points in the size of this vector L is the amount of wire exposed to the magnetic field, right? So the length of the wire in the field, the direction points in the direction of the current, and B again is the current that the wire is exposed to. So the more of the wire that's in the magnetic field, the stronger the force. The bigger the field, the bigger the force. The larger the current, the larger the force. And the current has to be flowing, to get the maximal amount out of this cross product, has to be flowing perpendicular to the magnetic field. And I can use, again, a right-hand rule to determine the F. I just align my index finger with the current, align my middle finger with the field, and my thumb is going to point in the direction of the force. So let's try that. Let's imagine that I've generated a magnetic field from this permanent magnet, and then I bring a positively charged particle into that field, and it's drifting forward with velocity v here. What direction does the force on that object point? What direction does the force point? Remember, the force is equal to QV cross B. All right, let's go ahead and end the poll. Most of you selected D. Let's use our right-hand rule. Our index finger points in the direction of QV. It's a positive charge, so that points in the direction of V, that points upwards. At that position where that charge is, the magnetic field is I'm gonna point my middle finger in the direction of the magnetic field. Now my